Hello everyone, and welcome to Electrochemistry, where chemistry meets electricity. In this 20-minute one-shot, we'll cover electrode potential, types of electrodes, the standard hydrogen electrode, and the electrochemical series. We'll then build Voltaic cells and tackle the important Nernst equation and the Gibbs free energy relation, delta G equals minus NFE. We'll also cover practical applications like batteries and fuel cells. To top it off, we'll solve 3 solved numericals on the Daniell cell and Nernst equation. This is the final physical chemistry unit. Let us master it. Hello students. Today we begin our journey into electrochemistry, a fascinating branch of chemistry that studies the relationship between chemical reactions and electrical energy. We can think of this relationship working in 2 main ways, which are represented by 2 types of electrochemical cells. First, we have the electrolytic cell. In this cell, we use electrical energy to drive a chemical reaction that wouldn't happen on its own, a non-spontaneous reaction. This process is called electrolysis. On the other hand, we have the galvanic cell, also known as a voltaic cell. Here, a spontaneous redox reaction produces electrical energy. Think of the batteries in your phone or remote control; those are galvanic cells. The key idea in both cells is that oxidation always occurs at the anode, and reduction always occurs at the cathode. Remember the mnemonic and ox and red cat. However, the charge of these electrodes is different. In galvanic cells, the anode is negative and the cathode is positive. In electrolytic cells, this is reversed; the anode is positive and the cathode is negative. Now, let's discuss electrode potential. Simply put, electrode potential is the tendency of an electrode to either gain or lose electrons when it's in contact with a solution of its own ions. Imagine dipping a metal rod, like zinc, into a solution of its salt, like zinc sulfate. An equilibrium is set up at the surface between the solid metal atoms and the metal ions in the solution. The potential difference developed at this interface is called the electrode potential. This tendency can be one of 2 types. First is the oxidation potential, which is the tendency to lose electrons and get oxidized. Second is the reduction potential, the tendency to gain electrons and get reduced. They are numerically equal but have opposite signs. So, the oxidation potential is the negative of the reduction potential. To compare different electrodes fairly, we use the standard electrode potential, which is measured under specific standard conditions: a 1 molar concentration of ions, 1 atmosphere pressure for gases, and a temperature of 25 degrees Celsius or 208 Kelvin. Electrodes come in various forms. Let's look at 4 main types you should know. The first, and most common, is the metal-metal ion electrode. This is simply a metal rod dipped in a solution containing its own ions, like a zinc rod in a zinc sulfate solution. The second type is the gas electrode. A great example is the standard hydrogen electrode, where hydrogen gas is bubbled over an inert platinum surface that's immersed in a solution of H+ ions. The third type is the metal-insoluble salt electrode. Here, a metal is in contact with one of its sparingly soluble salts and a solution containing the anion of that salt. A classic example is the calomel electrode, which consists of mercury, solid mercury 1 chloride, which is Hg2Cl2, and a potassium chloride solution. Finally, we have the redox electrode. In this type, an inert conductor like platinum is placed in a solution containing ions of the same element, but in different oxidation states, like a solution with both Fe2+ and Fe3+ ions. Here, the platinum simply facilitates the transfer of electrons. To measure any electrode potential, we need a reference point. That reference is the standard hydrogen electrode, or She. By international agreement, this is our primary reference electrode. So how is it constructed? The She consists of a platinum electrode which is coated with finely divided platinum, called platinum black, to increase its surface area. This electrode is immersed in a 1 molar solution of hydrogen ions, which is typically HCl. Pure hydrogen gas is then continuously bubbled over the electrode at exactly 1 atmosphere of pressure. The crucial point is this: By convention, the standard electrode potential of the She is assigned a value of exactly 0 volts at all temperatures. This arbitrary 0 point allows us to measure all other standard electrode potentials relative to it, creating the electrochemical series. Hello students! Today, we're exploring the electrochemical series. This is a ranked list of electrodes based on their standard reduction potentials. At the top, we find the strongest oxidizing agents, like fluorine with a potential of plus 2.87 volts. At the bottom are the strongest reducing agents, like lithium, with a potential of minus 3.04 volts. This series is incredibly useful for 4 main reasons. First, it predicts the direction of redox reaction species with the higher E0 gets reduced. Second, we can calculate a cell's standard EMF. Third, it determines displacement reactions. For example, zinc will displace copper from its solution. And fourth, it helps predict a metal's reactivity with water and acids. Now, let's look at the classic Daniell cell, a galvanic cell that generates electricity from a chemical reaction. It has 2 half cells. The anode is a zinc electrode in a zinc sulfate solution, where oxidation occurs. The cathode is a copper electrode in a copper sulfate solution, where reduction happens. A salt bridge, containing something like KCl, connects the two to complete the circuit. At the anode, zinc solid gives zinc 2 plus ions and 2 electrons. At the cathode, copper 2 plus ions plus 2 electrons gives solid copper. We write this using cell notation as Zn solid, pipe, Zn SO4, double pipe, Cu SO4, pipe, Cu solid. Its standard EMF is calculated as E0 cathode minus E0 anode, which is 0.34 minus negative 0.76, resulting in a positive 1.10 volts. But what happens when conditions aren't standard, like when concentrations aren't 1 molar? For that, we use the Nernst equation. This powerful formula calculates the cell potential under any non-standard conditions. Its general form is E equals E0 minus RT divided by NF, all times the natural log of Q, where Q is the reaction quotient. At 25 degrees Celsius, this simplifies to E equals E0 minus 0.0591 divided by N times the log of Q. For our Daniell cell, where N is 2, the equation becomes E equals E0 minus 0.0591 by 2 times log of the zinc 2 plus concentration over the copper 2 plus concentration. Essentially, the Nernst equation lets us find the cell's EMF at various concentrations. Finally, let's connect electrochemistry to thermodynamics. The relationship between Gibbs free energy, or delta G, and cell potential tells us about spontaneity. The key equation is delta G equals minus NFE. Here, N is the moles of electrons transferred, and F is the Faraday constant, about 90,500 coulombs per mole. For standard conditions, the equation is delta G0 equals minus NFE0. This also connects to the equilibrium constant, K. By combining it with the equation for delta G0 and K, we find that log K equals N times E0 divided by 0.0591 at 25 degrees. So, what does this mean? A positive E0 gives a negative delta G0 and a large K value, which means the reaction is spontaneous and strongly favors the products? Hello class, let's solve this problem. The question is, calculate EMF of Daniell cell at 25 degrees Celsius if Zn2 plus concentration equals 0.1 molar and Cu2 plus concentration equals 1.0 molar. Standard E cell equals 1.10 volts. Log 10 equals 1. First, let's identify what's given. E0 cell is 1.10 volts, zinc 2 plus is 0.1 molar, and copper 2 plus is 1.0 molar. For the Daniell cell, the number of electrons transferred, N, is 2. Now, we apply the Nernst equation, E equals E0 minus 0.0591 by N times log Q. The reaction quotient, Q, is the concentration of zinc 2 plus divided by copper 2 plus. So, Q equals 0.1 divided by 1.0, which is 0.1, or 10 to the power of minus 1. Substituting into the equation, E equals 1.10 minus 0.0591 divided by 2 times log of 10 to the power minus 1. This simplifies to E equals 1.10 minus 0.02955 times minus 1. The two negatives make a positive, so E equals 1.10 plus 0.02955. Therefore, our final answer is approximately 1.13 volts. The EMF is slightly higher than standard because the low concentration of zinc 2 plus favors the forward reaction. Well done. Now let's explore a fascinating type called a concentration cell. Here, both anode and cathode are the same metal, but they are in solutions of their ions at different concentrations. For example, a copper electrode in a 0.1 molar copper 2 plus solution and another in a 1 molar solution. The cell notation shows this difference, Cu pipe Cu2 plus 0.1 m double pipe Cu2 plus 1 m pipe Cu. Since the electrodes are identical, the standard cell potential, E0 cell, is 0 volts. The EMF is generated solely by the concentration difference. We calculate it with the Nernst equation, E cell equals 0.0591 divided by N times log of the cathode concentration over the anode concentration. The more concentrated side is the cathode. The cell operates until concentrations become equal. Batteries are practical galvanic cells we use daily. They are classified into two types. First, primary cells, which are non-rechargeable and discarded after use. A classic example is the Leclanche dry cell, with a zinc anode, a manganese dioxide and graphite cathode, and an ammonium chloride electrolyte paste. Alkaline batteries are also primary cells. The second type is secondary cells, which are rechargeable. We can reverse the cell reaction by passing an external current through them. The most common is the lead-acid battery in cars, with a lead anode, a lead dioxide cathode, and sulfuric acid. Other important secondary cells are nickel-cadmium, or NiCd, and the lithium-ion batteries that power our phones, known for their high energy density. Next, let's discuss fuel cells. Unlike a battery, a fuel cell converts chemical energy from a fuel directly into electricity, and it runs continuously as long as fuel is supplied. The most common is the hydrogen-oxygen fuel cell. At the anode, hydrogen reacts with hydroxide ions, H2 plus 2OH minus gives 2H2O plus 2 electrons. At the cathode, oxygen gas and water accept these electrons, half O2 plus H2O plus 2 electrons gives 2OH minus. The overall reaction is simply hydrogen plus oxygen gives water. These cells are highly efficient, reaching around 70%, and are completely non-polluting since water is the only byproduct. Because of these advantages, they're used in space missions and are a promising technology for electric vehicles. Finally, let's examine corrosion, a natural electrochemical process like the rusting of iron. In the presence of water and oxygen, mini electrochemical cells form on the iron's surface. Some spots become the anode, where iron is oxidized, Fe gives Fe2 plus 2 electrons. Other spots become the cathode, where oxygen is reduced, O2 plus 2H2O plus 4 electrons gives 4OH minus. The iron 2 plus ions are then further oxidized to iron 3 plus and form hydrated iron 3 oxide, which we call rust. How do we prevent this? Methods include galvanization, which is coating with zinc, cathodic protection, which uses a more reactive sacrificial anode like magnesium, or simply painting or electroplating to create a physical barrier. All right, class, let's tackle our first problem. We need to find the standard Gibbs free energy, or delta G0, for a cell. The question gives us the standard cell potential, E0, equals 0.34 volts. The number of moles of electrons transferred, N, is 2. And Faraday's constant, Fe, is 96,800 coulombs per mole. The key relationship here is the formula delta G0 equals minus NFE0. Now, we simply substitute the given values into this equation. So, delta G0 equals minus 2 times 96,500 times 0.34. When you multiply these numbers, you get minus 620 joules per mole. It's common to express this in kilojoules, so we divide by 1000. This gives our final answer, delta G naught equals minus 65.62 kilojoules per mole. Remember, the negative value confirms that this cell reaction is spontaneous under standard conditions. Now for our second problem. We are asked to calculate the equilibrium constant, K, for a Daniell cell at 25 degrees Celsius. We're given that the standard cell potential, E naught cell, is 1.10 volts, and the number of electrons transferred, N, is 2. At 25 degrees Celsius, we can use this key relationship, log K equals N times E naught cell, all divided by 0.0591. Let's plug in our numbers. Log K equals 2 times 1.10 divided by 0.0591. The numerator becomes 2.20, which, divided by 0.0591, gives us 37.22. So, log K equals 37.22. To find K itself, we take the antilog, which means K equals 10 to the power of 37.22. This is an astronomically large number. What does this huge value for K tell us? It means the Daniell cell reaction goes essentially to completion. At equilibrium, almost all reactants have become products. All right, class, a quick recap of electrochemistry. So to summarize, we have electrode potential, measuring the tendency to lose or gain electrons. The electrochemical series helps predict reaction spontaneity. More positive E naught means a stronger oxidizing agent. For non-standard conditions, we have the crucial Nernst equation, E cell equals E naught cell minus 0.0591 divided by N, log of Q. This is vital. Then, we connect to thermodynamics with two key formulas. For spontaneity, delta G naught equals minus NF E naught cell. Remember, a negative delta G is spontaneous. And to find the equilibrium constant, use log Kc equals N times E naught cell divided by 0.0591. Master these, and you're golden. Now for some exam tips. Pay close attention. A common trap is mixing up anode and cathode. Remember, oxidation at anode, reduction at cathode. Use the mnemonic and ox, red cat. NEB loves asking numericals based on the Nernst equation, so you must memorize it. A huge time saver for standard potential is E naught cell equals E naught cathode minus E naught anode. Don't flip the sign of the anode, just subtract it directly. Year after year, NEB asks for delta G or the equilibrium constant Kc from a given E naught cell value. Practice these conversions. Stay calm, read the question carefully, and you will ace this section. You've got this. And that's a wrap on electrochemistry. Fantastic job, everyone. Before you go, always remember the Nernst equation, E cell equals E naught cell minus RT divided by NF times natural log of Q. It's the key. If this video helped you out, please subscribe and hit that like button. Drop a comment below with the next chapter you'd like. Coming up next, we're diving into inorganic chemistry. Stay tuned and happy studying.